Welcome to the deep dive. Okay, let's jump right in. We're talking about something pretty fundamental in machine learning today, especially with these giant models, the transformers.
Yep,
It's
absolutely.
not just about getting an answer anymore. You need to know, well, how sure is the model about that answer?
Exactly. Think about critical applications, medicine, self-driving cars. Knowing the model's confidence or uncertainty is uh, non-negotiable.
And that's quantifying uncertainty. But it's tricky, right? Especially this epistemic kind.
Right. So you have two main types. Aleatoric is just, noise or randomness in the data itself. A blurry photo, maybe. Can't do much about that.
Okay.
But epistemic uncertainty, that's about the model itself. Does it know what it's doing in this specific situation? Has it seen data like this before?
So it's uncertainty from a lack of knowledge.
Precisely. And ensembles training multiple models are usually great for this. If they all disagree on an input, it's a good sign the models are like collectively uncertain about it. They haven't learned that part of the space well.
And that's been the traditional approach, explicit ensembles, kind of the gold standard.
It has been, yeah. You train, say, 10 different models, maybe with different random starting points, different data shuffles, then you average their predictions.
And the spread tells you the uncertainty.
Exactly. The variance between them. It's a simple concept.
And there's always a but with these huge models.
Yeah, the butterscotch. Imagine training 10, 20 versions of a model with billions of parameters.
Uh-huh.
The compute power, the memory, it just scales linearly. It becomes, well, completely impractical for most people, most organizations.
Right. So you need that uncertainty, but the best way is too expensive for the models everyone's using, these transformers.
That's the bottleneck. And, other attempts at parameter efficient ensembles haven't always worked well with the specific architecture of transformers or weren't really designed for them.
Which brings us to our source material for this deep dive, a paper on something called LoRA-Ensemble.
Yes, and it's a really interesting, quite clever approach to get ensemble-like uncertainty from transformers without that crippling cost. It's specifically designed for parameter efficiency in these self-attention networks.
So our mission today is to really unpack how it works, especially the innovative bits, the more academic details behind why it's effective.
Sounds good.
Okay, so before LoRA-Ensemble, we need to understand just LoRA, low-rank adaptation. This popped up for efficiently fine-tuning LLMs, right?
Exactly. LoRa came first. The key idea, the sort of insight, is that these massive pre-trained models are heavily overparameterized.
Meaning they have way more knobs than they strictly need.
Kind of, yeah. And when you fine-tune them for a specific task, the actual change you need to make to the model's weights often lies in a much, much smaller, lower dimensional subspace. You don't need to wiggle every single parameter.
Okay, so you're not retraining the whole thing.
No. Mechanically, LoRa works like this. You take an original weight matrix in the model, let's call it W, you freeze it,
Don't touch the original weights.
right? Then you add a small update to it, so the new weight W is W plus a W.
Okay, W plus a change.
But here's the low rank trick. That change, GW, isn't stored directly. It's factored into two much, much thinner matrices. Let's call B and A. So GW equals B times A.
Ah, like W is W plus BA.
Exactly. And the rank, let's say R, which is the inner dimension connecting B and A, is chosen to be really small, much smaller than the original dimensions of W.
So the only things you train are the parameters in B and A.
Precisely. Instead of trading millions of parameters in W, you might only train thousands or tens of thousands in B and A. Huge saving.
Makes sense for efficient fine-tuning. So how do they turn this into an ensemble? That's the LoRa-Ensemble innovation.
This is where it gets really neat. They take that LoRa concept and apply it within a single pre-trained transformer backbone to get multiple virtual models.
Okay, walk me through it. You start with your big pre-trained model of VIT for images, maybe BERT for text.
Yep. And step one, absolutely crucial, you freeze that backbone, all those W weights stay fixed.
Frozen backbone. Got it.
Then you look inside the self-attention blocks, specifically the linear projection layers, the query, key, value, and output matrices, WQ, WK, WV, WO.
Those are the core parts of attention.
Right. Now, instead of adding just one BA update pair to each of these W matrices,
They add multiple pairs.
exactly. If you want an ensemble of, say, 16 members, you create 16 separate pairs of B and A matrices, BAA, AAA, all the way to BAA for each of those attention layers, WQ, WK, etc.
Whoa, so wait, for ensemble member number 5, its effective query matrix is WQ plus BAA.
You got it. Each member uses the same frozen W backbone, but gets its own unique trainable Ben and Um matrices added on top in those key layers.
So when you feed an input through,
You essentially compute the output n times, once for each member, using its specific W plus n setup.
and the final prediction is the average.
Usually the average, yes, and the uncertainty. That's just the variance across those n different outputs. Standard ensemble calculation, like in their equation 4.
Okay, the elegance is that you only train those small binom sets. The parameter cost must be tiny compared to n full models.
Exactly. Table 1 in the paper shows this really clearly. For a VAT model with 16 member, an explicit ensemble needs 16 times the parameters. LoRA-Ensemble adds maybe, I don't know, 10–20% additional parameters on top of the single frozen backbone. It's a massive difference.
Okay, efficiency checks out. But here's the deeper question, the more academic puzzle, perhaps. How does just fiddling with these tiny Bama matrices tacked onto a frozen backbone actually create enough diversity, enough difference between the members to capture real epistemic uncertainty? It feels like they should all be pretty similar.
That's a fantastic question, and it's really at the heart of why this works so well. The paper dives into this, and a key factor seems to be the random initialization of the A and B matrices for each member.
Just like random starting points. That seems almost too simple.
It does, but think about what happens during training. They did analysis using singular value decomposition, SVD. You can see this in figures like figure 11. SVD basically finds the main directions or axes along which a matrix transforms data.
The most important transformations the layer performs.
Right. Now, when they looked at the singular vectors, these main directions of the trained LoRa updates compared to the original frozen W, they found something really interesting.
Okay.
The LoRa updates introduce what they term intruder dimensions. These new directions created by the BUA updates are almost orthogonal to the main directions of the original W.
Orthogonal, meaning like totally uncorrelated, pointing in completely different ways in the high dimensional space.
Exactly. The cosine similarity heat maps in figure 11 show this lack of correlation clearly. Each LoRa-Ensemble member, because it's Bun and all, started randomly and were trained independently, learns to modify the model's function along axes that are distinct from the original model and distinct from the other ensemble members.
Wow, so it's not just nudging the original transformation slightly, it's adding genuinely new, independent ways for the model to process information for each member.
Precisely. And they contrast this with explicit ensembles. Even though explicit members are trained independently, their weight updates tend to be much more correlated with the original singular vectors of the pre-trained model. They find different solutions, sure, but within a more similar subspace.
And the visualizations support this, the TSAE plots.
Yeah, figures 10C and 13 are quite striking. They plot the training trajectories of the model parameters. LoRa-Ensemble members spread out way more, exploring a much broader region of the lost landscape. Explicit ensemble members tend to cluster much closer together.
Which suggests LoRa-Ensemble members are finding genuinely more diverse solutions in function space.
That's the takeaway. The combination of the additive low-rank structure, the random initialization, and critically, the frozen backbone, forces each member down a unique path, creating these diverse, nearly orthogonal updates. That diversity in the weight space translates directly to diversity in predictions, which is what you need for good uncertainty estimates.
Okay, the academic explanation is compelling. It's a structural reason for diversity, but does it actually deliver in practice? Does it match or beat the expensive explicit ensembles on accuracy and, crucially, calibration?
Well, based on their experiments, yes, absolutely. And often it actually beats explicit ensembles, particularly on those calibration metrics. If you look through the tables 2, 3, 7, 9, 11, LoRa-Ensemble is consistently hitting state-of-the-art or very close.
Calibration metrics like EASE, NLL, Breyer score, those tell you if the model's confidence is actually trustworthy.
Exactly. EC, expected calibration error, is a big one. If a model says it's 90% confident, is it actually correct about 90% of the time for those predictions? Getting good EC scores, like they show on the HAM 10,000 skin lesion dataset in Table 3, is really important if you're thinking about, say, clinical use. They often get better calibration than the explicit ensemble.
With a fraction of the parameters and costs, the efficiency numbers back in Table 1 were pretty stark. Much lower parameter count, faster training, faster inference.
Yep, the savings are significant. There are some implementation nuances, like they mentioned using PyTorch's VMAP can add overhead, or needing to chunk inputs for the audio spectrogram transformer, which might affect wall clock time comparisons slightly. But the fundamental parameter in memory efficiency is undeniable.
And it's not just one type of model or data, they tested it broadly.
Oh yeah, it seems quite general purpose for self-attention networks. Images like CFAR, the medical AMAN 10,000, natural images on a naturalist, different sizes of vision transformers like D-Tiny, small, base in table 10,
Okay.
and then different modalities entirely. Audio classification on ESC50 using an AST, table 7, text sentiment analysis on SST2 using BERT, table 9. It holds up across the board.
That's pretty convincing generalizability. What about that comparison they did, LoRa-Ensemble versus just a single LoRa model, but with a really high rank?
Ah, yes, table 8. It's a really important control experiment. They took a single Loron model and increased its rank R so that the total number of trainable parameters, BA, was about the same as the sum of all the parameters and all the little Banach matrices across the entire Loron ensemble.
So same parameter budget, but structured differently, one big update versus many small ones.
Exactly. And the result, the single high-rank LoRa ensemble performed significantly worse. Both accuracy and calibration were lower than the LoRa ensemble.
So it really confirms it's the ensembling aspect, the diversity from multiple independent low rank updates that's driving the benefit, not just throwing more LoRa ensembles at the problem.
Precisely. It validates the core idea. Diversity through multiple, efficient, low-rank adaptations is key.
Let's circle back to the academic comparisons a bit. They contrasted LoRa Ensemble quite heavily with BatchEnsemble, or BE, another low rank idea, but it didn't perform nearly as well on transformers in their tests.
Right, tables 2, 3, and 12 show Batch Ensemble lagging significantly behind LoRa Ensemble on these transformer tasks. And the paper offers a pretty clear technical reason why. It boils down to how the member-specific low-rank parts interact with the shared weights.
Okay, what's the difference?
LoRa Ensemble, as we said, uses an additive update, W plus BA. Batch Ensemble typically uses element-wise multiplicative scaling. So the weight is like W shared element-wise multiplied, that's the A symbol, by some low-rank scaling factor, often based on rank 1 vectors R and S, like W share R.
Additive versus multiplicative. Why does that matter so much for creating ensemble diversity? Seems subtle.
The analysis in the paper, looking at the gradients, equations 10, 11, suggests that the multiplicative interaction in Batch Ensemble couples the learning of the member-specific parts, R and S, much more tightly to the shared weights, W shared. The gradient for R depends directly on the values in W shared.
Ah, so the path each member takes during training is kind of constrained or influenced by the shared part in a way that doesn't happen with the simple additive update in LoRa Ensemble. Reduces their independence.
That seems to be the issue. It potentially hinders the members from exploring truly diverse parts of the solution space. And they show evidence for this too. They tested a variant, Batch Ensemble plus Table 13, which uses the BE structure, but switches to an additive update, like W shared plus RC.
And how did that perform?
Much better than the original multiplicative Batch Ensemble. It confirms the additive approach is likely superior for diversity here, but interestingly, it still didn't quite match LoRa Ensemble's performance.
So something else about LoRa Ensemble's specific approach is still better. Maybe the frozen backbone.
Exactly. That seems to be the other critical piece. Remember we stressed freezing the backbone W. Table 11 shows what happens if you don't freeze it in LoRa Ensemble, if you let W train along with a bell and no matrices.
Performance drops.
Significantly. It often performs much closer to a single model or similar to the struggling Batch Ensemble.
Wow, so letting the main backbone learn actually hurts the ensemble diversity. How does that work?
The hypothesis ties back to those intruder dimensions. If the massive backbone is also learning and changing, it seems to overwhelm or wash out the small, diverse, orthogonal perturbations being introduced by the individual LoRa matrices. The model finds a path dominated by the backbone updates, causing the different members to effectively collapse towards a similar solution, losing their distinctiveness.
So freezing the backbone is not just for efficiency, it's actually a mechanism to preserve the diversity generated by the random initializations and the additive low-rank structure. It forces the model to rely on those unique intruder dimensions.
It really seems that way. It's a fascinating interaction. The frozen state actively enables the diversity mechanism. Quite counterintuitive, but strongly supported by their experiments.
Any other sort of finer points or limitations worth mentioning from the paper?
Yeah, a few interesting details. They explored the impact of a LoRa rank, R figure 9. It acts as a kind of tuning knob. Sometimes higher rank helps accuracy, but might slightly hurt calibration, like on HM1000. Other times it helps both, SFAR 100. So it's dataset dependent.
And that connects to whether the base model is under or overconfident.
Right. They note that for models that start underconfident, like VE on CFAR 100 sometimes, ensembling might initially make calibration metrics like ECE look worse because accuracy improves really fast, maybe faster than the confidence ratings catch up. But for models already prone to overconfidence, ensembling seems to reliably improve calibration. It relates to work on things like double descent in large models.
So context matters. It's not always a simple more ensemble members equals better calibration story.
Precisely. They also briefly mention initialization strategies for B and A matter a bit for the final balance, though several reasonable strategies worked well, Appendix K, Table 15.
And limitations.
Well, the main practical one is compute time at inference. While you save massively on parameters in memory, you still technically need to perform a forward pass for each of the n ensemble members to get the final prediction and uncertainty. So inference latency still scales with n.
Right, it's not magically free.
No. And the current method uses a fixed set of n members. They suggest future work could explore treating the LoRa parameters probabilistically, maybe allowing sampling from a distribution over LoRa updates to get potentially infinite virtual members.
Okay, so wrapping up this deep dive, we've looked at LoRA-Ensemble. It seems like a really smart way to get uncertainty quantification from huge transformers without paying the huge cost of explicit ensemble.
Yeah, the core idea is elegant. Freeze the giant backbone and then add multiple small, independent, low-rank LoRa updates within the attention layers for each member.
And train only those small matrices. The result is state-of-the-art accuracy and, importantly, calibration, but with drastically fewer parameters and faster training. Plus, it works across different types of data and transformer models.
And the academic insight is key. The additive nature, the random initialization, and the frozen backbone work together to create genuine diversity through those nearly orthogonal intruder dimensions, which is why outperforms methods like BatchEnsemble, where learning dynamics get coupled or diversity gets washed out.
It's a great example how understanding the structure of these models allows for targeted, efficient solutions to big problems like uncertainty.
Absolutely. Which leads to a final thought for you, our listeners. We know trustworthy AI is becoming more and more critical. We need models we can rely on, especially when the stakes are high. Given that methods like LoRA-Ensemble make robust uncertainty estimation practical and affordable, even for massive models, how might this change the pace at which we deploy AI in sensitive domains? Could this be a key enabler for building more trust in these complex systems?